Hello everyone, it's Proof Architect here again today. And now, kind of in a follow-up to my showing that we can rotate the complex numbers just by multiplying them by I, I'm going to go and see what happens if I were to go and multiply all of the complex numbers in the four quadrants of the Argand diagram with just an ordinary complex number. Let's do it where both the real part and the imaginary part is positive. So I have real, z1, be positive, and imaginary, z1, be positive. And let's just see what we get. So we do z1 times z1, that's just a plus bi, times a plus bi, bi squared. And now we just FOIL. So a squared plus abi plus abi, so we get 2abi. And then we get plus b squared I squared, which just simply becomes a squared minus b squared, the difference of two squares, plus 2abi. So technically you have a real part here, which could be positive or negative depending on whether a or b is greater than the other. And the 2abi is positive, so this imaginary of z1 will always be positive. That much we can say. And this guy, for the real part, it just depends on our choice of a. So I would say for now it's positive if a is greater than b. Otherwise, to have it reach the other zone, as we kind of like suggested last time, otherwise we will get that it's less than 0 if b is greater than a. Let's do z1 times z2 now. z1, z2. a plus bi times minus a plus bi. Here I get minus a squared plus abi minus abi. This is where it gets a bit interesting, and then we have plus b squared I squared as well, which means we simply get minus a squared minus b squared in general. So very oddly, z1, z2 by this calculation will always belong to the real numbers. And there's no imaginary part. There's no imaginary part, so imaginary is 0. No, yeah. z1, z2 equals 0. So this is purely a real number, which means that if we were to take the z1 and multiply it by z2, our projection should bring us somewhere along the real number line, this guy. So that's kind of interesting, I find. And now let us do z1 with z free. I need space here. Hope this works. A plus bi. And then z free minus a minus bi. And then minus a squared minus abi minus abi minus b squared I squared. So this becomes positive, so it's b squared minus a squared minus 2abi. So we know that the imaginary part of z1 and z free is always negative. And the real part, I'm just going to write ... junk now, will be positive if b greater than a, otherwise opposite sign if a less than b. And so finally we have the fourth one, z1 times z4. z1 times z4. So this is a plus bi. And now I have a minus bi. And because it's a conjugate, sorry, not yeah, because it's conjugate, we get a difference of two squares. So a squared plus abi minus abi, so those parts cancel out. And all we just get is minus b squared I squared. So we get a squared plus b squared. So z1, just like before, z1, z4 is an element of the real numbers, and actually I should say it's the positive real numbers, if I could do it like this. For this guy, on the other hand, it will always be the negative real numbers. So yeah, very surprisingly, z1, z2, it will map to, so let me be even more precise, not only does z1 being multiplied by z2 map it to the real numbers, it maps it to the left-hand side, the left-hand axis of this Argand diagram. If I do z1 and z4 on the other hand, it maps this to the right-hand side of the Argand diagram. So if you watch my video or understand that imaginary numbers under multiplication form a cyclic group of order 4, then the reason why we end up with like imaginary part of 0 when we multiply these two complex numbers z1, z2 and z1, z4 together is because, well, basically we're giving like different rotations, and these rotations just happen to map to a multiple of 180 degrees or multiple of pi, and another multiple of 360 degrees or 2 pi radians. And if you want to go and like show this rigorously why it's true, then and you're not satisfied with the Cartesian notation of it, then you have to go and appeal to polar form notation, where we talk about angles in general. So the polar form of a complex number is just z of r of theta. It's a multivariable function where we have r times cosine of theta plus I sine theta. And basically you have to multiply these two, basically multiply a copy of this with one angle theta 1 with another copy with an angle theta 2. And that's going to be a horrendous computation to fill out. You will then, so I'm not going to do it, but I will just say all you need to do is, once you do it and look at your garbage, you have to eyeball and see that you end up with this kind of like term over here, or this, which essentially corresponds to compound angle addition identities for sine and cosine. And things to make note of in case you're dealing with angles of different signs is that cosine, as always, is an even function, which means that if I add in a negative input, it does nothing to the sine at all. However, sine is an even function, which means if I add in a negative input, then it will make the output negative. So keep this in mind, and this will change the result of what this actual formula looks like. But you have to go backwards, go from something very complex, and then simplify to this lesser complex stuff. And so you can conclude in general that this following principle, the argument principle for complex numbers, argument is just complex number term for angles. You get that the argument of any two complex numbers being multiplied together is equal to the sum of their arguments. So the argument of a product of complex numbers is the sum of the arguments of those complex numbers. Hope that makes sense for you. And so yeah, let's just do an example just to make things like really intuitive. Say if I have a complex number z1 and I just have that its theta is like, say, pi over 4. I'm going to work in radians, sorry degree people, team radian, team pi radians over here. And then I have z2 correspond to theta 2, which equals, let's see, pi over 4, no, 2 pi over 4 gets me pi over 2, so this is 3 pi over 4. Well, then the argument of these guys, z1, z2, yeah, will just correspond to basically this angle, theta 1. This is basically arc of z1. This is arc of z1. And this is arc of z2. And so you get theta 1 plus theta 2, which is essentially pi over 4 plus 3 pi over 4. You have a common denominator. That's just 1 pi plus 3 pi's. That gives you 4 pi's over 4. So we end up with pi. Similarly, if you were to do this with, say, like 45 degrees, and then we do it with, what's 360 minus 45? I don't know. I'm going to do it in terms of, okay, 3 pi over 4. I get 5 pi over 4 over here. Okay, you're good. We get 7 pi over 4 over here. So we take 7 pi over 4. 5. Fail. Epic fail. Pi over 4. And then theta 2 equals 7 pi over 4. Now I just add those two angles together. So theta 1 plus theta 2, that equals argument of z1 plus argument of z2, which just gives me pi over 4 plus 7 pi over 4, which gives me 8 pi over 4. And that gives me 2 pi. So voila, indeed, for this case, you map it to the right-hand, sorry, for this example, you map it to the left-hand side of the horizontal axis. For this, you map it to all the positive real numbers on the right-hand side of your axis here. And so, if you want, you could perhaps find a way to go and make this argument rigorous, that like you'll get imaginary, that for a certain selection of I and j over here, you could perhaps make some rigorous argument that the imaginary component of zij, zij is always 0, mixing and matching depending whether I or j is an odd number or an even number. So you can probably make some rigorous argument like that, which is compatible with one of these 4 combinations, and get it to work. But yeah, that's basically it so far. So I hope you enjoyed this video, fellow architects, and until then, I wish you a pleasant day.